So we're going to start chapter 2, which is forces and vectors, or vectors and forces. Here. So, and this is going to be a very, very quick chapter. So the first thing we need to talk about is how do you set up a coordinate system in terms of say X, Y, and Z. And there's basically two steps. Step one, choose the X. So if you have a potential coordinate system here, the X, it's a free choice. So if we just go and take the standard one, once we decide that's X, then the rest of it is all determined by your right hand. So what do? So here's my right hand, and so what one would do here is you point your right hand in the direction, you can see where the X is going, and then you roll your fingers, and they will roll towards the Y, and your thumb will point in the Z. So if my hand is pointing out here, the fingers will roll to the Y, and this is Z coming out of the page. All right. Now, if on any problem as we go through the semester, if you set up a coordinate system where you were using your left hand and your fingers roll to the Y and your thumb points in the Z, that'll be a left-handed coordinate system. If you ever set up a left-handed coordinate system, the problem is 100% wrong. Okay? Absolutely no left-hand coordinate systems. I will not tolerate that. You are being told now. All right? There have been very nasty engineering accidents because people have used left-handed coordinate systems. Why is that? Picture a large project where somebody uses a left-handed coordinate system and nobody realizes it, and they take the results and they expect something to go to the left and it goes to the right, and bad things happen. All right. I have never professionally come across left-handed coordinate systems. People always set them up right-handed. Having said that, if there is one criticism I have of our textbook, this is it. As we move forward, and especially for the mechanical engineering students, as you go into dynamics, they use left-handed coordinate systems all the time, which is just not the standard. It's just not done. I don't know why they do it, but anyway, for our class, here's the rule. Don't ever do it. Okay, so in the world of vectors, we have the concept of a scalar. So what is a scalar? Hopefully you're familiar with that. It's just a magnitude. All right. And so it's the distance between two objects. So there's 100 kilometers between Fredericton and St. John. It's just a magnitude. All right. What's a vector? Hopefully, and this is incredible review. So a vector is a scalar and a direction. Or we may just put in here a magnitude and a direction. So when I say St. John is 100 kilometers to the south, that describes a vector from Fredericton to St. John. Okay, so hopefully that is familiar to everybody. Then when we deal with vectors, we have to, given a vector, so if I'm given some vector here, and I'll give one in a moment, we need to be able to break that vector down into its magnitude, an angle, and a unit vector. These are used to describe direction often, though you also get direction out of angle as well. So suppose I have, we'll just set up your basic XY coordinate system. So this is X, so let that be Y. And here's my given vector, I'll call that A, where if we were to bring a point down here and a point there, say, suppose that was 4 and that's 3. Okay, not to scale, I'm not going to worry about that. So as a vector, we would say the vector A is 3 in the X plus 4 in the Y. And, oops, went too far here, wasn't thinking. So here's A, goes from O, put the A in here. So we have 3x plus 4y there. All right, magnitude of A. So hopefully we all know we simply take the x component, square it, the y component, square it, take the square root. And we come up with 5. The angle, all right? The angle is always measured counterclockwise off the horizontal in an xy coordinate system here. All right, so if I do that, then the angle associated with, don't need the bar over this because this is a magnitude. All right, so the angle associated with A would be the inverse tangent. So its height is 4, the run is 3, so inverse tangent of 4 on 3. And that would take us to 53.1 degrees. Okay, so hopefully you're all familiar with that. And then the unit vector A, so I'll have UA. So this is a vector. So a unit vector based on A is simply 1/5. So we divide by the magnitude of A, and then we would have, 3x plus 4y. Or we could write it as 3/5 x plus 4/5 y. And so this is a unit vector. It goes in the same direction as A, but its magnitude is only 1. Okay? So these are often called direction vectors. Okay? So that's 2 dimensions. So what happens when we have more than 2 dimensions? Let's say we have 3. So suppose I have a vector B, and it's given by 4x plus 2.5y plus 5z. It could happen. All right? And maybe that's in meters. Put a little dimension on it. And so what's the magnitude of B? Well, as you add more dimensions, it just extends the same equation we had before. So now it would be 4 squared. Let's put a magnitude of B. Plus 2.5 squared plus this third component. If we had a fourth component, we'd say plus that squared. If there's a 5th dimension, which we're never going to have in our class, we'd say plus that squared, yada, yada, yada. Anyway, so for 3 dimensions, which we will come across, take the square root of that, we get 6.874. So it just extends in the very natural way. All right, the unit vector. Same idea. We'll just divide by that. So the unit vector would be, it's just easier to write this way, 1 on 6.874, 4x plus, 2.5y plus 5z, and we can add our little meters on the end. And we can put our meters here too. All right, so that's our unit vector along the direction of B. Now, if I was to multiply this through, and I'll actually just write that out, okay, for reasons I'll describe in a moment. So there's our unit vector written that way. But let's just compare that to this one. All right? And I'm going to draw this bigger here. 1, 2, 3, 1, 2, 3, 4. So there's a vector A. All right, so this is 3, and that's 4. Reasonably to scale. All right, so let's think about this. 3/5, what is that? Well, this is dimensions 3, that's 4. The hypotenuse there would be 5, right? All right, so 3 over 5, that would be, if take that as theta there, that would be the cosine of theta. All right, and so if you think of, now, if let's call that theta, let's call this one over here alpha. So if we think, let's see what we have here. Okay, relative to this angle, so off the y-axis, this is 4, this is now 3 up here, the cosine of alpha is 4/5. So the angle, when we form our unit vector, these coefficients with the x, y, and z, those are cosines off of the axis. Cosine theta, cosine alpha. This is the same thing down here. All right? These are all cosines. But it's what we have here, it's the cosine of the cone angle. Kind of an interesting concept. So I'll just say this is next to impossible for me to draw, but let me hopefully give you an idea what I'm saying. So we had our vector B, get the magnitude, divide by that, we have our unit vector, and these are all cosines associated with different cones. So if this is x, this is y, that's z, so we could have a cone coming off the x like so, and we could have another cone coming off the y, and another cone coming off the z. And the intersection of all these cones would actually give us this. Okay, so this is describing the cosine of the cone angle associated with x, the cosine of the cone angle, and so that would be coming off, call that, say, theta, this coming off alpha, this one coming off, I don't know, beta, whatever you want. Okay, these are the cosines of the various cone angles for each respective axis, which then describes the vector. All right, so we have in this first, I'm going to actually stop this video here. So it's going to take us 3 videos to knock off chapter 2, which is forces and vectors. So I don't want, you probably don't like to have really massive long videos. It's easier to watch a series of short ones, so that's what we'll try to do. And when you're ready, come check out the next one. Catch you soon.